Alright, so thanks for the invitation to speak in the seminar. So everything I will talk about today is joint work with Zhiwei Zheng. So first, I will talk about singular sextic curve and the symmetric tubular fourfolds. So in modular program, we always want to do commutations, and there are many ways to do commutations. One way is JIT commutations for modularized programs, and this one corresponds to like adding some degenerated varieties in the family. And so for the boundary component, we have some modular meaning, and there's another commutation like Bailey-Borel communication or toroidal communications. So it's a communications of commutation symmetric space, locally commutation symmetric space. So our goal today is to compare these two commutations. So in many cases, we can identify the JIT commutations of a modular problem with Bailey-Borel commutations. So that's our goal. So let me give you first example. So we'll focus on sextic curves. So we fix a characteristic complex vector space, dimension 3, and we consider M is a moduli of smooth sextic curve. So we take smooth 6 forms with the quotient. So this is the moduli of smooth sextic curve. So it has a very natural JIT commutation, which is just a JIT quotient. So from general theory, we know the smooth sextic curves are JIT stable, and we need to add other stable points and also semi-stable locus. So that's a JIT commutation. And we also have something in between. So M1 is a sextic curve with simple singularity. With APE singularity. And, from sextic curve, we can construct a K3 surface using double cover over P2. So yes, for any smooth sextic curve, we can consider a double cover over P2, which is branching over curve C. So this is K3, smooth K3 surface. And if we take the hyperplane class, so H for back of hyperplane class, then self-intersection is equal to 2. So we get a family of degree 2 K3. And we can consider the period map for degree 2 K3. So let's fix some notation. So the middle cohomology will give us K3 lattice, which is just this one. It has signature 319, and we take the complement of H. Then the period domain for K3. It is one connected component of So it's a type 4 domain, type 4 Commission symmetric domain with dimension 19. And this has signature 2 in it. Okay. So if we use a period map for SC, we will have a map from M to some arithmetic quotient of this type 4 domain. And if you count the dimension, this has dimension 19, and we get open embedding. So the theorem of Shar says that we can extend this map to set curve with ADE singularity. So P extends to one to some hyperplane arrangement, and this is an isomorphism. So the image here is a complement of some hyperplane arrangement. Some hyperplane arrangement.
I'm sorry. What is the group gamma?
Gamma, yeah, it's an arithmetic group acting on D. Actually, it's a, let's see. So here, it's an automorphism group of lambda fixing H. It's an index 2 subgroup such that fix this locus D. So
can we see what it does to the sort of K3 surface? That, I mean, does it replace it with another one that's similar, or?
Oh, so it's just related to the marking of your K3 surface. So whenever you choose this isomorphism, it's up to a choice of automorphism. And then when you form the period map.
Okay, so it's only after we're doing it.
Yeah. The H is a hyperplane arrangement. And we can describe the locus of the image of sextic curve with ADE singularity. And Shar also described what's the difference between M bar, which is a JIT computation, and Bailey-Burrell computation. So it's included in this diagram. So it's birational. And we have a space called M tilde. So on the right-hand side, we can form the Bailey-Burrell computation. And on the left-hand side, we can form the JIT computation. And there is a space which sitting in between, and we can have explicit description for these two maps. So let me write it here. So the first map, M tilde to the JIT computation, is a blow up along some special point. So let's say omega here is a semi-stable point correspond to the triple product of a smooth conic. So S is smooth conic. And it's a semi-stable point with closed orbits. This one is a blow up at omega. Sometimes it's called a current desingularization. And the other map to the Bailey-Burrell computation is related to the hyperplane arrangement. So it's a minimal blow up. Such that the hyperplane arrangement become Cartier near infinity. Remember, Bailey-Burrell computation usually is very singular, and if we take a divisor here, H mod gamma, sometimes it's not Cartier. But we can do some desynchronization. For example, we can do toroidal computation, then the closure must be Cartier. But now we need something in between, like between Bethe-Borel computation and toroidal computation. So we can summarize these two steps, like this desynchronization, like this blow up and blow down, in a more uniform language. This was done by Loyangha. So he considered type 4 domain or hyperbolic pole. B is any type 4 domain. Or hyperbolic pole. And H is some hyperplane arrangement. And we have some arithmetic group acting on D. So he considered this computation of the hyperplane arrangement. So first we have the Bethe-Borel computation. We do some blow up. So this is called a symmetric blow up. It's something between Bethe-Borel computation and toroidal computation. And the construction is the same as toroidal computation. Like you look at infinity and you look at the cone there, you need to do some cone decomposition. And this one is a minimal blow up such that the hyperplane arrangement is Cartier at infinity. And then we contract this component. For example, here, when we do the blow up of omega, then the exception divisor is exactly identified with hyperplane arrangement. So it is an exception divisor. So here, when we do this blow up, then we can contract this divisor here. So this is contraction along D direction. So of course we get some computation of the hyperplane arrangement. So let's call it Loyangha computation. So if we use this language, then Sharp's theorem can be stated as isomorphism between JIT computation and the Loyangha computation. So Sharp's theorem just says that we have JIT computation here and also Loyangha computation. So what we will do today is to establish more isomorphism of this type. And we can also have criterion like when is this Loyangha computation is exactly Bethe-Borel computation.
In this case, it is for K3.
For K3, this is not Bethe-Borel.
So for K3s, it's not a Bethe-Borel, but then how do you get from Sharp's theorem to this version?
So I replace this blow up and blow down operation by Loyangha computation. So finally, I have isomorphism between JIT computation and Loyangha computation. So maybe I didn't get your question.
I just don't see how you went from that version of Sharp's theorem. How did you deduce?
So Sharp's theorem says that we have a birational morphism from JIT computation and Bethe-Borel computation. And it goes in this diagram, like we first blow up at boundary and then contract the hyperplane arrangement, the divisor corresponding to H. And Loyangha computation is a general computation for any complement of hyperplane arrangement. First do blow up and then do blow down. So it's exactly this diagram. So finally we have this isomorphism.
Remind me, please. I've asked you this before. Remind me what's it what's the type-fold domain?
Type-fold domain. It's any domain of K3 type. So if we have some lattice of signature to n, and we consider the positive lines in this lattice, isotropic positive lines in this lattice, and then it's a type-fold domain. Just correspond to the point structure of K3 type.
Just SO2 and module maximum combined.
Oh yeah, just write it here. So it is type-fold. So it corresponds to when n is odd and even, it corresponds to type B and corresponds to thinking diagram B and D. All right. So first, let's talk about singular sextic curves. So another example. It's just 6 lines in P2. So the moduli space is a JT quotient of P B star. We take 6 copies and we do the JT quotient by SLV, and also we can alternating all the lines. So this is a permutation group of degree 6. And when we do this JIT construction, we need to specify the polarization. So when we change the polarization, the JIT quotient may be different. So in this case, the polarization is the most symmetric one. So it's a box product of O1. And then we view 6 lines as a degree 6 curve, singular degree 6 curve. So it's just a union of these 6 lines. And when we do the double cover along singular sextic curve, we get a singular K3. So we will have same double cover, but we need to resolve the singularity to get a smooth K3. And when we do this 6 lines for generic position, we will have 15 nodes. So we will have 15 nodes. So it corresponds to E1 up to E15 exceptional divisors. So it corresponds to this 15 P1 on our K3 surface. And also we have the pullback of O1. So we have rank 16 sublattice. And if we denote M to be the fixed sublattice by the deck transformation, then it also has rank 16. So actually, it's generated by these 16 curves, and also adding the image, the pre-image of all these 6 curves. So it's a saturated lattice, saturated lattice of the lattice generated by E1 to E15 and H. Now our D is a type-4 domain. Corresponds to M per. So the dimension of D is 4. And we use this M polarized K3 to form our period map. So theorem by Matsumoto, Sasaki, and Yoshida. The theory is that the period map can extend to the JIT quantification F, and it forms the Bailey-Burrell computation of dimension 4 type 4 domain. So this is an SMO. So there are many other examples of this type. So our first main result is to generate this to any singular, to sex curve with any singular type. So let me state our theorem. So we fix an integer from 0 to 15, and we consider sigma n is a sex curve with n nodes. It may not be connected, so we take a connected component. So it's smooth, but it may not be connected. So this is one of the connected components. And we take the normalization of the closure of sigma. Since it's a normalization, it has a natural polarization coming from the ambient space. And our first theorem is the JIT quotient is isomorphic to the Loyang computation of a type 4 domain. And we also have a criterion when this is Bailey-Burrell. So this is Bailey-Burrell. If the special point omega is not contained in this singular type. So for example, if we consider this kind of example, like partition of 6, n1 times 1, n2 times 2, n k times k equal to 6, this is a partition of 6. And we can consider degree 1 curve, degree 2 curve, and degree k curve. So C is a union of some smooth curves with degree 1 to up to k, and multiplicity n1 up to nk. So we can describe sigma tilde quite explicitly in this case. So it's a product and the JIT quotient is just SLV times the product of permutation groups. So this is an F. So we identify this with type 4 Loyang computation of type 4 domains, and we have 11 examples of this type, and 8 of them are Bailey-Burrell. So this includes some examples studied by Laza and his students. Any question for this part?
can you say anything about why some of them are Bailey Burrell and some aren't?
The criterion is very easy. So, for example, if we consider 2, 2, 2, and we have a partition of 6 by 2, 2, 2 here, then F cube is in this type. So that's why it's not Bailey Burrell. But if we have like the first example 1, 1, 1, 1, 1, then F cube is not in this type. So our next topic is about cubic fourfolds. So the first example comes from degeneration of sextic curve or degeneration of K3 surfaces. So we can consider cubic fourfolds. So let's reset our notations here. Now V is a dimension 6 complex vector space, and we consider M to be the modular space of cubic fourfolds. And we can consider the sublocus, which consists of smooth cubic fourfolds, and also cubic fourfolds with AD singularity. And from for smooth cubic fourfolds, we still have similar results like K3 surface. We have the global Torelli theorem. So let me first state what is the global Torelli theorem. So for any x, for any smooth cubic fourfolds, we consider the middle cohomology. The whole numbers are 0, 1, 21, 1, 0. And here you have the square of hyperplane class. And we fix this data. Let's say this is equal to a square. It's isomorphism. Now lambda is a lattice of signature 21 cubes. And we consider the orthogonal complement of H squared. Then the type 4 domain is similar. So it's one of the connect component of isotropic line. So we can also take gamma to be an index 2 subgroup of automorphism of this abstract data. So it's an index 2 subgroup which fixes this D component. And the global Torelli theorem proves backward down. It's just saying that the period map from M smooth to this symmetric space, locally symmetric space is an open domain. So that's a global Torelli theorem for smooth cubic fourfolds. Later, Laza characterized the image of this period map. So let me summarize their results. So they're saying that P extends to modular space of cubic fourfolds with AD singularity. And the image is also the complement of some hyperplane arrangement. And further, we have identification of M bar with the Loyama computation. So that's the main results we want to use for cubic fourfolds. So we will consider some special subfamily, which is the cubic fourfolds with specified symmetric type. Let's see one example.
Sorry, you said this is a characterization of the image?
So Lada characterized the image of image of period map of smooth cubic fourfolds is a complement of two hyperplane arrangements. And then he proved that this P extends to AD singularity, like fill in one part of the hyperplane arrangement. So in his notation, it's like the image of smooth as D minus H2, H6.
The AD singularities are four-dimensional?
You mean
These guys, yeah.
the modular of AD singularities? You
No,
mean the total dimension or-
these are fourfolds with AD singularities.
Yeah, this could be a fourfold with AD singularity. It's just keep adding square terms for the usual AD singularity.
And you don't allow the velocity to collide.
No. So it's just isolated AD singularities. Because from definition they're isolated.
And what's the dimension of the moduli space?
It's D is the dimension 20.
That's the same as the dimension of the modular fourfolds.
Right.
So
This is
an
an
open
open
subset, and you're just saying what it's complementing.
Say that again?
So the image is just an open subset. It's a risk open subset.
Yeah, of some hyperplane arrangement complement. So another example comes from symmetric cubic fourfolds.
Can you say what that arrangement is, or it's not nice?
So it's explicit, like you mean the hyperplane arrangement, right?
Yeah.
So they are called this name because they're the fixed point of some reflections determined by some root vectors with length specified. Yeah. So like some -2 or -2. Sometimes the signature is confusing. Yeah. So some vectors with depth intersection 2 or 6, I believe. So there's a complement of those vectors. Oh, sorry, it's a orthogonal complement determined by those vectors.
And you don't know how to extend the map further, so it actually be subjective.
So it cannot be subjective here. It's we have to contract the part comes from like so for this H2 here we can fill in by AD fill in by cubic fourfold with AD singularity. So they're not that bad. So degeneration of whole structure is actually good. So it's just the monodromy is just some determined by some sextic group. So
And what's the geometry around H1?
so the other parts is more mysterious. So if we do this Loyama computation, we do some blow up there, and then the divisor corresponding to H1 gamma is actually supposed to be the modular space of degree 2k3. So the dimension is 19 there. So the missing data is like you do some blow up for moduli space of you do some blow up for this GIT along some locus, and then the exception divisor exactly corresponds to degree 2 K3, and the construction is actually geometric.
But aren't the degree 2 K3s already in there?
You mean
Aren't they
in
one of the Hassett divisors? Already in the smooth part?
why is it already in the smooth part?
If you take cubic fourfolds contained per plane, isn't that also the degree 2 K3s?
Maybe they sit in there in some other way.
Yeah, maybe they sit in there.
Yeah, so geometrically, how to realize this H as degree 2 K3 is like the moduli meaning for those cubic fourfolds is that cubic fourfolds singular along some curve, and then you do some blow up or construction, or you look at the tangent cone of those singularities. Then in some way you can recover the degree 2 K3. Any other question? All right, so let me say something about the symmetric cubic fourfolds. So there's a construction by Alok, Carlson, Toledo. So they consider cubic threefolds determined by F. So and for cubic threefold, we can associate a cubic fourfold. It's just a branch carrying of P4 branching along this cubic threefold. And say X. So this cubic fourfold has a symmetry of a cyclic group of order 3. So this acts on X. And we take the trivial character. And we can look at the action, corresponding action on Hodge structure of X. We look at H4, C. So the part fixed by chi has dimension 11. So in the Hodge number like 1, 1, 1, then correspond to 110 part. So it has a Hermitian form with signature 110. So if we consider the period map for this subspace, then we will have a map from, let's say, so first, let's say this F is a moduli of a smooth cubic threefold. And the period map F to this ball complex, a ball of dimension 10 with an open embedding. And what they prove is this map actually, let's say, the image is also a complement of hyperplane arrangement, and we have isomorphism of GIT computation and the Loyang computations. So we can generalize this to cubic fourfolds with any symmetry, finite group symmetry. So generalization is like we fix this is any finite subgroup such that fix some smooth F. With three forms. So when you fix this, then we know AX on F is equal to some character of A, lambda is some character. And we can take the eigenspace, lambda eigenspace of A, just any F, such that A small a, sorry, and so on F is equal to this character. We can also form JIT communications. So first, we need a group. So this is usually the normalizer of A in GLD. So when the character is trivial, it's a normalizer, but when it's not trivial, it's just some finite index subgroup of normalizer. Then we can also form the JIT quotient as P B quotient of by. So our main theorem is again isomorphism between this JIT communication and Lorentz communication. Now D is type 4 or hyperbolic 4, depending on the character of the group action on this H22 H31 part. So let me give you more examples of this type. So this example was studied by Greg Pearson and John in 2017. So they consider a pair of hypersurfaces and cubic threefold. So for cubic fourfolds of this type, you have a symmetry of D2. And in this case, identify this modular space. It's actually isomorphic to D4 cross the symmetric 3, D4 quotient out by SL5. And now we need the polarization since it's a product. So it's O1 box product with O3. And the result is that this JIT is actually isomorphic to the Bailey-Borel computation of some type 4 domain. And we can get these results just using this more general theorem and also a criterion for Bailey-Borel computation. So we have another criterion for Bailey-Borel. it's more complicated, but in many cases we can compute this criterion explicitly. So if we consider A is a cyclic group of prime order, this is a prime, then we will have 13 examples. So there's a classification of such prime order group acting on smooth cubic fourfolds. So there are 13 examples, and 4 of them gives us a hyperbolic ball, and 8 of them are type 4 domain. And 1 of them is just a dimension 0 with isolated points. And also 7 of them are Bailey-Borel quantifications. So we have a complete list for prime order automorphisms. So any question about this theorem?
So there's a big literature about automorphisms and prime order automorphisms of K3 surfaces. Do those all embed into the cubic fourfold moduli or no?
So for, let me see, there's some subtlety here. So if you restrict to smooth degree 2 K3 surface, then I believe is all included in, wait.
But there's some pretty exotic things that
Right.
has to do with one of the large finite simple groups.
So there's a classification like they can be embedded into.
It's one of the exotic groups from the finite classification. Mathieu group maybe?
Matthew 24.
Yeah. So there are a lot of different groups that occur. Do you see all of those? Can you lift all of those out from cubic fourfolds?
Yeah, I don't know, but my collaborator is working on this direction with Lada. So they have a similar result for cubic fourfolds. So they can embed automorphisms into the one of the conway groups. And actually, except 2 of them, other automorphisms can also be embedded into Matthew 24. So I think their paper will appear soon.
Okay. So the 13 examples that you have, those are the only prime cyclic groups
Yeah, prime cyclic groups
that can act on any cubic fourfold?
acting on smooth cubic fourfolds.
Acting in a particular linearly or
Linear.
any
So
action?
there are all subgroups of GRP. So we have theorem like smooth cubic fourfold, the automorphism must come from the projective transformation.
Just because it's kind of anti-canonically embedded or something.
So for degree high enough, it's always true for hypersurfaces.
Keep going.
So let me say something about the proof. So idea of the proof just comes from the functoriality of GIT and the Loyang quantifications. So we have GIT constructions coming from this symmetry type or degeneration type. And we can always prove this map is finite. And the domain here is normal variety. And use results by Shar or Lada, we know we have isomorphism to Loyang quantifications of this type 4 domain. And on the right hand side, we prove some functoriality between these 2 Loyang quantifications. So this involves some detailed analysis of constructions of Loyang quantification. So it's similar to the functionality for toroidal computation. So for the base space, you have some fan decomposition determined by the hyperplane arrangement, and then you prove that this cone decomposition also induces a cone decomposition for the subspace. So we have this finite map. And the original period map gives us a bimorphic morphism from the smooth locus to the target. So this comes from a toroidal theorem, a global toroidal theorem for K3 or a global toroidal theorem for cubic fourfolds. And then we have two finite maps, and then we count the dimension as maps to the same locus here. Then we can extend this finite map to a real isomorphism. That's basically the idea of the proof. So we can also combine these two constructions, and we can consider also symmetric singular sextic curve. So we have a similar theorem that uses this proof, and this gives us more examples of identification of GIT quotients and also Bailey-Burrell complications of ball type or type 4 domains. Any questions?